In today's lesson, we are going to learn about covalent bonding. So far in this unit, we have focused on ionic bonding, which deals with a metal and a nonmetal. That is, it contains one thing from the left side of the stair-step line and one thing from the right side of the stair-step line. Now what we're going to learn about today is going to be covalent bonding, which is two things from this right side of the stair-step line. That is, two nonmetals. If you think back to the inquiry lab that we did, that was where we split everything in two groups. One of those groups was ionic, the other group is covalent, and we're now going to learn about that second group. The thing I want you to be most careful about with these notes is going to be one of the last slides in here is going to show the difference between ionic and covalent bonding. It is very, very important that you are able to determine the difference between them and remember the differences in determining chemical formulas and how to properly name them. So the slide in here that focuses on the comparison and the difference between ionic and covalent bonding, please pay very close attention to that slide. It's about 4 minutes long, but it's going to apply to this entire unit. So one of the differences with covalent bonding is that the atoms now share the electrons, whereas in ionic bonding, one electron was taken. So notice here with the electrons being shared, nothing is becoming an ion. Nothing's gaining a positive charge, nothing's gaining a negative charge because nothing's taking or losing electrons. What the electrons actually do is they spend their time orbiting essentially between the two different atoms. So the electrons are shared in this case. And then again, this occurs between two nonmetals, so that is two things on the right side of the stair-step line, or don't forget about hydrogen. Hydrogen is also a nonmetal. When we learn about covalent bonds, there are two different types of covalent bonds, right? One type of covalent bond is what we call a polar covalent bond. And a polar covalent bond, and just to tie in everyone's favorite dog analogy, this is when the electrons are shared unequally. That is technically one of the atoms actually wants the electrons more. So think of it as kind of winning the tug of war over the electron. One thing you're going to want to focus on here is if you look at fluorine on your desk, and this only works on your desk, it doesn't work on the green periodic table, there's this part where it shows fluorine has this 4.0. That is what's called electronegativity, and you can think of that as how badly an atom wants to gain an electron. So fluorine having that 4.0 is the highest electronegativity of any element. If you look at the noble gases on the far right side of your periodic table, you'll see they're all 0 or have a dash. That is because noble gases are happy. They don't want electrons at all. If you look on the left side of your desk, you'll see lithium has like a 1.0. Well, lithium doesn't want electrons, so it has a low number. Lithium's actually trying to get rid of electrons. So anyway, polar covalent is where atoms share electrons unequally, and we'll learn more about this in a couple slides here. In a non-polar covalent bond, this is where the electrons are shared equally. That is, both things are pulling with equal strength. So that is, if two dogs of equal strength were to try fighting over a bone, well, neither one of them is going to win. They are equal strength. As I mentioned a few slides ago, there is what is called electronegativity. So electron negativity is essentially electron greed, as you can tell by this crazed guy up here with the money. It's kind of that same idea. It is how greedy an element is. So the higher the electronegativity, such as I showed you with fluorine, the more that it wants an electron. And the difference in electronegativity between atoms will predict their type of bond. And we'll look at this on the next slide. So what these types of bonds refer to is the difference in electronegativity for the two atoms that are bonded. So the nonpolar covalent bond we learned about was when they were equal strength. That is an electronegativity difference of 0. So that would be if you look at like two oxygens. If they were to be sharing their electrons, well, your desk shows you that they have an electronegativity of 3.5. But if they're both pulling with that, electronegativity strength of 3.5, the electrons are going to be shared equally. That is, they have no difference in strength. So therefore, they are non-polar covalent, and electrons are shared completely. They spend as much time with one oxygen as they do with the other. In a polar covalent bond, that is if the difference in electronegativity is between 0 and 1.7. For the most part, this is going to be two nonmetals, and that is an unequal sharing of electrons. Electrons are still shared, but it is not equally. So that would be if you had sulfur and fluorine bonded together. Sulfur has an electronegativity of 2.5, fluorine has an electronegativity of 4.0. The difference between them in this case is going to be a difference of 1.5. Since that falls within this range of 0 to 1.7, these are going to be considered polar covalent bonds. And then the last type of bond, and this is the ionic bonds that we learned about over the previous few days, that is when electronegativity is greater than 1.7. That is, well, essentially at that point, the electron is just said to be transferred. So the electron is essentially transferred in that case because it's going to spend so much time with one of the atoms. So again, if like fluorine and lithium were bonded, well, fluorine has an electronegativity of 4.0. It really, really, really wants electrons. Lithium, on the other hand, has an electronegativity of 1.0. As we've learned, lithium doesn't want electrons, it's trying to get rid of them. So therefore, these would have a difference in electronegativity of 3.0, which is definitely greater than this 1.7. So therefore, that is what we consider an ionic bond. Now, some of you might notice, if, let's say carbon were to bond with beryllium. Well, carbon is a nonmetal looking at your desk, whereas beryllium is a metal. The difference in their electronegativities, however, is only 1.0. Does that mean that carbon and beryllium create a polar covalent bond? Well, kind of. These ranges aren't perfect, but just to simplify things, we're going to stick with if there is a metal present that is something on the left side of the stair-step line, it is automatically ionic. Don't worry about these electronegativity differences. If there is two or more nonmetals, that is two things from the right side of the stair-step line, or don't forget hydrogen is still a nonmetal, then it is automatically covalent. So simplest thing, metal is ionic, two or more nonmetals is covalent. Do not stress about these ranges. What I would ask that you please do now is to pause the video and discuss with the person next to you or whoever you're working on these with different examples you have of these covalent prefixes. So where have you heard the word mono before? What other words? Or di, tri, tetra, and so on. And then when you are done discussing with the person next to you, you can play this video again and I will go through some examples that students will commonly use. Now that you have had a chance to discuss these prefixes with the person next to you, let's take a look at some of these or come up with examples of some of them. So if you look at the word mono, some very common ones that students think of when they hear the word mono would be like a monocle. So that is one eyeglass piece, or a monopoly is when a company wants to own all of the properties or all of the business. Die is usually a little bit trickier of ones for students. It is not related to dice in any way that I can think of. I actually think students usually have trouble coming up with die. If you do know one, you should let me know. Tri is pretty simple. Tri meaning three is going to be like a triangle, except for this thing doesn't like to let me type very well. So that'd be a triangle. Tetra, what a lot of students will actually say for this one is Tetris, which is true, and students usually just aren't sure why. The reason that tetra and Tetris are related is if you look at Tetris pieces, they will all be made up of 4 blocks. So no matter which Tetris piece you look at, they always consist of 4 individual smaller blocks. So that is how tetra and Tetris are related. Penta is going to be like a pentagon, so it has 5 sides. Hexa is the prefix for 6. For some students, they'll just say heptagon to remember 7. I mean, hepta doesn't have a whole lot of other uses that I'm aware of. Octa, one of the most common ones for 8. Octa is an octopus, like it has 8 tentacles. Nana, the only thing I've ever really seen students be able to come up with this for one is instead of like Nana, they think of it like Nina. I don't know. It works. And then Deca actually has quite a few, so you can think of this like being a decade or a so a decade has 10 years, or a decathlon would have 10 events. Sorry, I accidentally capitalized the A there. But those are just some ways to remember it. Otherwise, you don't need to have these memorized. If you look at the top of the green periodic table, they are not on your desk. I have those green prefixes there at the top for you. So these do not need to be memorized. However, it is always good. I mean, it's going to make your life a lot easier if you can remember them. Alright, now is where things start getting very, very confusing for students. Now is where you're going to start mixing up your rules for ionic or covalent compounds. The first thing you need to do when you look at a compound, and you're going to see this on your ionic versus covalent compounds worksheet, you need to first determine, is it ionic or is it covalent? If it's ionic, it contains a metal. If it's covalent, it's 2 or more nonmetals. When you are naming covalent compounds, first thing you need to do, write the name of each element. Second thing is add prefixes to show how many atoms. Last thing is change the end of the last element to an IDE ending, so that rule is actually the same as it is for ionic. And then the fourth thing is if the prefix mon is not used for the first element listed. And let me give you an example that ties in all 4 of these rules. If I gave you the compound CO, okay, well, step number 1 says to name each element. So you would write this out and you would say carbon and then oxygen. Then it says add prefixes to show how many atoms. Okay, so looking at our prefixes from last slide, we have 1 carbon, so we would say mon carbon, and then we have 1 oxygen, so we'd say mon oxygen. Step number 3, add the last element, end the last element in "ide." So similar to as we did before, it's no longer oxygen, it just becomes oxide. And then step number 4 is the one that tends to confuse students. But this is why I use this example, is because you guys haven't heard of carbon monoxide. What you have heard of, though, is carbon monoxide. So what this 4th step means is if this first word contains mon, you just simply get rid of the mon. However, if mon is on the second word, we still use it. So the first word can have prefixes except for mon. So you could have like dicarbon monoxide, tricarbon monoxide, and so on. You just get rid of mon if it's on the first word. And we've all heard of like carbon monoxide poisoning. That's essentially what this is. It is 1 carbon bonded to 1 oxygen. Now I would like you to please pause the video and try solving these 4 on your own. Okay, now that you have tried these out on your own, let's go through them together. So step number 1 says that you need to write the name of each element. So if I go through and do that, P is going to be phosphorus. Sorry, I know my handwriting is terrible. You guys are probably used to that by now. And then O is oxygen. Step number 2 says that we need to add in our prefixes based off of how many of the atom there are. So in this case, we have 2 phosphorus, so that is going to be diphosphorus. 5 oxygen is going to be pentoxygen. And realistically, I should be able to fit these directly in front of the elements. I'm just not leaving myself enough room. Step number 3 then says we change change the second element to an IDE ending. So this is no longer oxygen, it is now oxide. ide. And then step number 4 says if mon is on the first word, we need to get rid of it. In this case, we have di there. So diphosphorus pentoxide is our correct answer. All right, taking a look at the second one. First thing we do is write out each element. So we would have carbon, and Cl is chlorine. So we have carbon and we have chlorine. Second step says that we need to add our prefixes. Since we have no number here, remember no number means 1. We just don't write the 1 in chemistry, so this is going to be mon carbon. And then since we have 4 chlorine, that is going to be mon carbon tetra chlorine. Step number 3, we need to change the ending of the second one to an IDE ending, so therefore this is now tetrachloride. And then step number 4, if mon is on the first word, we need to get rid of it. So in this case, the correct answer is going to be carbon tetrachloride. For the third one, step number 1, we need to write out each element. So this is phosphorus. Second element is chlorine. Step number 2, we need to add our prefixes. So this is mon phosphorus, since there is 1 phosphorus, and then trichlorine, since there are 3 chlorines. Step number 3, change to an IDE ending. And then step number 4, get rid of mon if it's on the first word. And so your final answer for this PCl3 is phosphorus trichloride. And then, looking at the last one, we have nitrogen, and we have oxygen. Step number 2, we need to add our prefixes. Since we have 2 nitrogens, that is the prefix di, and we have 1 oxygen, that is the prefix mon. Step number 3, we need to change to an IDE ending. So therefore, it's no longer oxygen, is now oxide. And then step number 4, if mon is on the first word, we need to get rid of it. Since mon is on the second word here, it stays, just like it did in carbon monoxide. And so our final answer for N2O is dinitrogen monoxide. Now please be very, very careful with these rules when you are doing ionic versus covalent naming. Remember, when you're naming an ionic compound, you simply write the name of the metal, write the name of the nonmetal with an IDE ending. Now in covalent bonding, you have to use these prefixes. So again, first thing you always need to ask yourself, is it ionic or is it covalent for which set of rules you're going to use? I feel like it is very important that we take a minute to recap on the difference between ionic and covalent, because this again is going to tie into the entire unit. And you need to be able to get very good at doing this. So, ionic bonding is what we learned about the first few days in this class. Covalent bonding is what you learned about today. And we need to be able to differentiate between them. So, ionic bonding always contains a metal. That is, it always contains something on the left side of this stair-step line here. Again, hydrogen is a nonmetal. So, ionic, if there's a metal present, it's automatically ionic. And then that metal has to be bonded to a nonmetal because you need a positively charged, that is something that wants to lose electrons, to bond with something that wants to gain electrons. You do not use any of those prefixes. You didn't see prefixes until today's lesson. Prefixes are not used in ionic bonds. You need to balance charges. Example of that is if I gave you something like magnesium bonded to chlorine. Well, magnesium has a +2 charge. You can see that looking right here. Chlorine, on the other hand, has a -1 charge. And so in order to find out that formula, you simply need to balance these. You're like, okay, I have 2 positive charges, 1 negative charge, so I would have a formula of MgCl2 because I have 1,2 chlorine in order to balance out charges. And then in ionic bonds, electrons are going to be taken. When you name something like this, That is, when you name an ionic compound, you write the name of the cation. So in this case, I would write out magnesium. And remember, your cation is always listed first. And then you write the name of the anion with an ID ending. So this would simply be magnesium chloride. However, if we were to look at a covalent bond like we learned about today, it is going to consist of two nonmetals. So again, two things from the right side of the stair-step line, or hydrogen. You have to use prefixes, so you have to use these prefixes at the top of your green sheet. You do not need to balance charges. These are all negative charges. You can't possibly balance them out to equal 0. Plus, the electrons are shared, not taken. So this one, you don't balance charges in a covalent bond. When you are naming something like this, so if I gave you, let's say, N2O5, well, you would just write this out as dinitrogen. Again, we're having to use those prefixes. We have two nitrogens, and then O5, and realistically that 5 should be a subscript. Since we have 5 oxygens, that is pentoxide, because we still need to have that IDE ending on our second word. The last thing I just want to introduce to you really quickly today is going to be at the top left corner of your green periodic table. You'll see a list of what are called diatomic elements. We're not going to do too much with these yet. I just want to introduce them to you because they are all nonmetals. Basically what they are is they are elements that cannot exist as a single atom in nature. They will always be bonded with themselves. So you can never have just one hydrogen atom. You can never have just one iodine atom or one bromine. If you had something like NaCl, sure, you can have one chlorine because it's not by itself. It is bonded with a sodium. However, if you wanted to have just chlorine, such as chlorine gas, that is always going to be a chlorine bonded to another chlorine. So therefore, it is always two atoms bonded together. A couple different ways that you can remember this. One is a lot of students use this mnemonic, hi Broncliffe. I don't know, like you're saying hi to your friend named Broncliffe. Another way that you can remember it is there are 7 diatomic molecules. So there are these 7 different diatomic molecules. You will see that they create this 7 on the periodic table, and then hydrogen is always kind of the oddball out. So a couple different ways to remember them, or they are at the top left corner of your green periodic table. And then really quick, here are the sources for my pictures.